me talking and you cannot hear me, please raise a hand. Chai, who is helping us with the techniques, could resolve it.
We can hear you clearly, Clemens.
Great. Okay, so my name is Clemens Röttgermann, now from Exina, which is a function safety and cybersecurity consulting company, but I spent several years in semiconductor verification specifically, so it's one of my interest areas, and I'm very happy here to share the session. First topic we have is a novel approach to reuse firmware for verification of controller-based subsystems using PSS. And the speaker is Vishnu Ramadas from Samsung Semiconductor in India. Hi, Vishnu. He basically has a focus, what I understand from his CV, on virtual prototyping, verification methodology, and performance estimation. Performance estimation, of course, is quite hot topic as the complexity and the performance requirements is increasing. So Vishnu, welcome to the stage. Vishnu, I will give you a short hint in terms of timing after, when do you want it? After 15 minutes, okay? Then you know that you have 7 to 10 minutes left for your talk. And so that because I think the nice thing about the presentation and about the conference is that we still keep interactivity. So I want to keep some space for questions at the end. Okay, so welcome, Vishnu. Please go ahead. I will go on mute.
Thank you. Can you see my screen?
Yes.
Yeah.
Yes.
So, welcome all to the presentation on a novel approach to reuse firmware for verification of controller-based subsystem using PSS. The agenda for today's talk is, sorry, I'm not able to, having some technical difficulties at my end. Yeah. Sorry, my PowerPoint seems to be stuck.
You'll just want to click one time on your desktop.
Okay, now it works. Yeah. So sorry for the delay. The agenda for today's talk is first going to start with looking at current verification challenges. Then it will move on to an introduction to what PSS is all about. And then we'll look at a few challenges that happen with the PSS model development and how some of these challenges can be overcome by reusing certain firmware APIs. Finally, we will move on to how this whole PSS model was validated and then the results and conclusion of our study. So during the SoC development cycle, there are tests at various stages of this development. First, there are certain verification tests at the IP stage when the model of that stage is ready. And once that has been integrated along with other IPs and interconnects into a larger SoC, there are verification tests run at that end as well. And later, when the emulator release is available, a few C-based tests are run then. And once the silicon is available, post-silicon validation is also done. So this rigorous set of tests is required to ensure that this SoC functions as required along all these stages. But one issue with having so many different testing layers is that the engineer has to write and maintain tests at each of these different levels. This leads to a lot of redundancy and a lot of extra effort on the engineer's part. But between the IP and SoC stages, there is, however, some reuse that is possible. But unfortunately, only a few scenarios are reused in this manner. A significant effort is also needed to add new scenarios, especially IP to IP scenarios. Moreover, the dependency on the IP DV team for any scenario input leads to very high wait times at the SoC stage. By the time the emulator is ready, there is literally no reuse possible between the SoC DV and emulator stages, primarily because the platforms are entirely different. This means that the engineer has to write a test from scratch to describe the very same scenarios that were tested on the DV front. So how can all this effort be reduced? How can we introduce some reuse such that the effort spent writing, maintaining, and testing these scenarios is less? PSS, or Portable Stimulus Standard, is a methodology that provides a solution to this. Now with PSS, one can describe the device in that abstract top-level implementation that is agnostic to the actual test platform. With this model, one can always generate tests that can work on varieties of platforms like emulation, C-based platforms, or RTL simulation. This can be done in 3 distinct steps. The first step is obviously to create the PSS model itself. The PSS model contains a list of attributes, that is an abstract representation of what all the device can do, and a list of constraints that help a PSS generation tool to ensure that the tests are generated such that they are part of the legal configuration space. The second distinct step is to write a scenario, which is essentially the same as fixing the values of certain attributes, such that they describe a particular test intent. The PSS tool takes these scenarios, randomizes all other attributes such that they fit the constraints, and generate an exhaustive list of tests that fill the entire configuration space with legal scenarios. Now, once these scenarios are ready, they can either be in a C-based form for emulator and silicon, or they can be in an SV test format and for SV-based verification. We will, however, focus more on the C test code because C test codes can also be reused for the RTL development by using direct programming interfaces to invoke required SV tasks. So once this test is ready, they can be compiled along with APIs. This forms a third distinct step. These APIs are nothing but a set of code that takes these generated tests and programs the target platforms as required. The APIs can also do much more complex tasks apart from direct register programming, which include monitoring the state of execution, handling errors if there are any, taking care of all the various state machines involved and making decisions on the fly. So to develop this PSS model, the engineer will first have to identify a list of attributes and constraints that make up the PSS model. These attributes roughly correspond to high-level control registers that exist in the device under test. And it can also correspond to certain high-level features that can be boiled down to multiple registers. Constraints, as mentioned earlier, help generate legal values for all these attributes. The developer will later design a set of APIs that, apart from handling register writes and reads, can also handle IP to CPU, CPU to IP communications, and may also have certain complex decision-making capabilities depending on the complexity. Now, although PSS, when adopted, helps create a streamlined, uniform way of generating tests to be run across a variety of platforms, adopting it is not very straightforward. There are certain challenges that come with it. The first of these is that people will be mostly writing PSS models for proprietary IPs. Unfortunately, they don't come with ready-made PSS utilities or standard libraries that service these. Also, at times, there is no base class to inherit from in these cases, and therefore development has to be from scratch. While this is probably a minor issue, developing PSS models and APIs for complex IPs could be effort-intensive and time-consuming. Depending on the complexity, the entire model could run into thousands of lines of code, making both maintenance and debugging a bit of a challenge. This therefore adds significant overheads to the development, validation of the model, and also acts as an barrier to adopting PSS. In addition, complex IPs will require the model developer to be well aware of the intricate details of the IP and able to handle its nuances pretty well. So how can we reduce this effort that invariably comes with developing PSS models? For example, if the IP is a fairly straightforward one, you can write a script in the language of your choice to generate an exhaustive list of register rights that directly program the IP and execute it as needed. But for slightly complex IPs, let's say there is a submodel that has a controller sitting inside it, this particular approach cannot be followed because the controller expects register rights in a certain order. And since the controller exists because it has to make intelligent decisions on the fly, the APIs will also have to be adaptive enough to deal with it. Therefore, a single dump of register rights will not help. In this case, certain existing test code can be reused to avoid developing these APIs from scratch. Now, what can be a good object for reuse? One example is a functional C model. A C model is basically nothing but a functionally accurate C++ or C-based simulation of this IP. And it comes with its own test bench, hardware model, etc. So under certain conditions, this test bench, which has already been proven to effectively handle this controller-based complex IP, it can be reused such that it meets our PS's needs. So under what situations can this firmware code, which I will refer to as a pseudo driver code later on, how can it be reused? Before that, let's take a look at a controller-based subsystem, a generic subsystem. In such systems, a specific firmware is needed to program the hardware which sits on the CPU that is inside the subsystem. During this firmware verification stage, a functional model that I mentioned earlier will be used to avoid dependency on RTL development so that firmware verification can happen independently. By reusing this firmware for the controller and reusing the pseudo driver code that already exists as part of the functional C model setup, PS's API generation can be optimized. As an example, let us take the case study of a video processing sublog that I worked on to prove this concept. So without going into too much architectural details about the video processor, it can be said to be a controller-based system with various subcomponents for hardware acceleration. This controller firmware that resides in the CPU is used to control encoding and decoding of multiple frames of video over a variety of codecs. This firmware, in addition, also programs the subcomponents intelligently on the fly as per the desired use case and execution state. It also monitors the status of various subcomponents to ensure correct execution, and in case of error, it corrects the path and cleanly exits or handles the flow. Now, this C model requires a particular input file, which is a text input configuration file that contains a list of attributes and the values. This is read by the firmware pseudo driver code, and the values are extracted and stored in certain data structures, which are used to later perform, which are later used to drive the controller. This controller acts as the interface between the hardware and the external world and drives the underlying hardware properly. As mentioned earlier, this flow is primarily used just to test the firmware before actual hardware is available. But for our integrated PSS model that should work on all platforms, the pseudo driver code and the CPU firmware can be suitably reused. Now, before we move on to the reuse, there are certain differences between this model environment and target platforms that need to be highlighted. First, the C model does not contain registers or memory in the true sense of the word. What I mean by this is that in C model, registers and memories are not modeled like the real world is. And in fact, they are rather modeled as C++ classes and the member functions. Any register associated functionality is a functional callback. So the C model driver code is written in such a way that this is kept in mind. However, in emulation or simulation platforms, this approach will not work as the registers or memory accesses there are much closer to reality. Second point of difference is that the C model code contains heavy dynamic memory allocation functions for handling various buffers that are necessary to operation. These buffers, these memory allocation routines need not necessarily work on simulation or emulation platforms, as the very nature of memory in these are different. For example, in the emulation, the kernel itself does not support all C++ libraries, and therefore one will not be able to compile these for that. And in simulation, the memory model itself is different. A third point of deviation is in how input is processed. In the C model, like mentioned earlier, it is through a simple configuration text file, which is read and parsed at runtime. However, as we saw earlier, for the PSS flow to work, it needs a C text file that is generated by the tool. Therefore, the input parser will have to be suitably modified to make use of this. One saving grace with this adoption is that the CPU firmware code can, however, be reused directly as long as it is being compiled with the right compiler version for the core. For our cases, we use the particular ARM version, and by using its associated compiler, the firmware code was ported onto both the emulation and the simulation platforms. The modified pseudo driver code should continue to interact with this setup seamlessly as it is inherently designed to operate with the firmware. Now we move on to a few code snippets that detail how these modifications were made. For example, in the C model, register accesses, like mentioned earlier, directly access the C++ class structures. For example, given the required address, it accesses the member variable of the required class and updates its value in case of writes. And in case of read, it returns the associated register value. Any function callback, any callback functionality is modeled as a C++ function. When we move on to emulator or simulation platforms, this approach will definitely not work. In emulation, the registers are exposed as direct memory regions for the CPU to target, and therefore it requires a direct memory write using pointers. In case of simulation, direct programming interfaces can be used to model SV tasks that write to the RTL model. And based on the target platform during compilation, you can provide the required compiler flag, get the version of the code that you need and run it. Note that the original C model register updation is also presented so that this flow works across not just the emulation and simulation, but also on the functional model, making it reusable by all stakeholders involved. When it comes to reads, it's pretty much the same story. Emulation makes use of direct pointer accesses to return the value. Simulation makes use of SV tasks to get the data. And C model makes use of register access models that are already present. Now moving on to the second point of deviation, memory allocation is a very important part of this entire flow. The pseudo driver code has to create buffers, update the firmware about these buffer locations, and then hand over control to that. The firmware and the hardware will interact with this buffer for sharing certain metadata, input, output images, and the like. Since malloc cannot be directly reused, a suitable alternate needs to be found. For our case, a very simple function did the deed. In our case, we wrote a function that just returns an address to a region in memory, region in the DRAM memory, and this address is used as the base address for the buffer. Address region overlaps are avoided by ensuring that this pointer is increased by the size of the buffer and handled accordingly. Definitely more complex things can be, more complex functions can be used if needed, but this serves the task for most applications. The third major point of difference is, as I mentioned, in the input configuration file. In the C model flow, the input is mainly text-based and the file has names of the attributes followed by the values. When it comes to how the C model views this, the test bench reads this, parses all the names of the attributes, extracts the value needed, and stores it in a structure that holds values for all bit fields. The firmware driver code later on uses these bit field values to program the registers, make decisions, etc., etc. But this approach will definitely need modifications when it has to be used with the PSS code. Right, for starters, the PSS test file generation is a C-based test as already mentioned, and an init function in it stores values that describe the test scenario into a different class. So members of this class again describe the test scenario and have to be used to program the DUT. Now, one way that this can be done is by reusing the same parser mechanism where it parses, extracts these names, and assigns these values to
Vishnu,
the C model.
sorry for the interruption. You have 5 minutes left.
Okay, I'll speed up.
So you have to get the feeling for your timing, right? So you spent 20 minutes, 5 minutes left. Thanks.
Thank you, I'll speed up. But however, this extraction requires a lot of overhead, and a simpler method will be to directly assign these values to the C model structures, which the C model will later use to program the test bench as required. So after all these changes are done, the model is ready for deployment. Before deployment, it has to be validated to make sure it works as expected. Now, how can this be validated? The best way to do this is to first run this, to generate a scenario, run this on the target platform, get the output file and compare it to a golden reference file. If the comparison passes, we know that this model works as intended for this particular scenario. Running it for a lot of scenarios will increase the confidence we have in our model. But then how do we generate this golden reference file that needs to be used? So when the scenario is generated with the PSS tool, it can also be directed to dump a text file parallelly along with the C test file. This text file can be in the format of the C model config file. This can be used with the IP functional model, and whatever output you get is treated as a reference golden. Since the functional model is functionally accurate as the name suggests, this output is expected to be the same as what the actual device should churn out. Now, once we have this output file, we can use the C test that was generated earlier, compile it with the APIs for the required target platform, load it onto the platform and execute it. This execution should result in the output file at a particular region in memory. Now, comparing that region in memory with the reference output should tell us if the comparison was successful or not, if the test was successful or not. An alternate to comparing large files is to compare the CRC values of these two, which will speed up the time. Now, this procedure was followed for the video processor we were discussing about, and it was tested for all the various codecs in both the encoder and decoder flow, and they were found to match on both emulator and simulator. Thus, with these minimal changes, we were able to create a model that works seamlessly on different platforms and gives out the output as expected. Moving on to the benefits that this flow has, it is not very beneficial in developing the PSS model as such, because the attributes and constraints are fairly independent of the actual target platform. It took roughly 2 days to list down attributes and 3 days to list down constraints, build the model and generate tests. However, the major benefit is seen when it comes to developing the driver code and validating it. We had earlier estimated 15 days to develop the driver code and 25 days to validate it. And this was on the lower side, and our targets could very well have exceeded this. However, with reuse, we were able to develop it in 3 days and validate it in 5 days for all the formats. It took roughly 3 days only because we had to find out the correct mapping between the attributes and whatever the C model uses, the bit fields that C model uses. Apart from that, everything else was straightforward and didn't take much of our time. Now, concluding this, PSS does make reusing tests across platforms easier during verification. It provides a very systematic way of generating tests that can be reused across various platforms, right from the functional C model, emulator, simulator, virtual prototyping, any platform, the silicon, and it can be run on each of these without much extra effort. However, model development and validation time is high for certain complex controller-based subsystems. This can be reduced by reusing pre-existing test code that is in use elsewhere. This whole process of adopting PSS and adopting test code for reuse as APIs reduces redundancies that can occur while maintaining test benches for various platforms. It can also speed up the whole process of development, as earlier mentioned. But one small problem associated with this is that some firmware test benches are available only during the later stages of development. Therefore, a left shift in the pseudo driver code to post-silicon test benches is needed so that PSS model development can also start early, and the firmware is also ready early so that everything can be integrated in the beginning and taken forward so that there is maximum reuse of tests and maximum efficiency that follows. So this brings us to the end of the presentation. Listed here are a few of the references that we followed during our study. And thank you all for attending. I'd be happy to take any questions at this stage.
Yeah. Well, thank you very much, Vishnu. We are pretty good in time, so there are 5 minutes left for some questions. And so I invite you to take the opportunity, as we are live here, to bring up some questions. I'm patient. I'm sure there are some questions. If no one has a question, I would like to raise two.
Sure.
So, one, have you applied the scheme to other IP or mainly to the video processing?
We did develop PSS models for other IPs as well, but most of those IPs are not as complex as this video processor. So for those IPs, we used a simple script to just generate the list of register writes required at the correct order, and we programmed it. But since video processor is slightly special in that it has to take care of the state of the operation, it has to be aware of whether the block is reading metadata on the 5th frame or on the last frame or exactly, we had to follow this new approach. So I see a question, what was the process to derive the PSS model from the existing code? So like I mentioned, there are 2 stages to this. The first is that you have to write a constraint and abstract model. This fairly depends on the kind of IP description documents or the knowledge of IP that we have and the register model, etc., where you identify certain top level configurations, like for example, in this case, what video codec it takes, what format it takes, what are the final fine tuning parameters, how many frames does it have, etc. That make up the PSS attribute model. Constraints are basically mathematical equations that describe how certain other attributes depend on each other and therefore make sure that no illegal scenario is generated. And the second part is the APIs, which, like I just mentioned, would be very complex, very difficult to develop from scratch for such a complex model. Therefore, we had to reuse this pseudo driver code that was being used for firmware verification, the controller firmware verification. We had to adapt it to suit our needs as presented, and the entire flow worked.
Okay, yes, I do not see another question. I would like to raise my second question. So I tried to understand in which way your PSS approach is differing from, because what I mainly saw is an abstraction of the register interface so that you can remap to the different platforms basically and environments, and that you did something similar for the memory access. So in which way does the PSS approach distinguish itself from basically an API abstraction level in the test bench?
PSS, as far as PSS is concerned, it is just concerned with creating the test. You have a model, you use the tool to create a test. You create a scenario, you create the initial C file that contains the values of attributes. APIs that I talked about are something that is decoupled from the PSS as such, but need to be used in unison so that these attributes can be used to program the DUT. PSS as such does not care about the implementation of the device. It just turns out legal attribute values based on the mathematical model you created. But along with the APIs, you actually drive the device. Okay, the question is, how do you verify your PSS model? In order to be sure that it is well defined. Yeah.
This is the last question, right?
Yeah. So like mentioned, we first generate this golden file by running it with the C model. Along with the C test, we generate this text file, the configuration file, run it with the C model, get the output encoded output MPEG file or bitstream or whatever it is, compile the C model for running on, let's say, an emulator, and then run it on the emulator, get the output image, compare both, and if the comparison passes, you know that your model works as expected. You do this for thousands of tests in a regression, and then your confidence increases in the model. So I hope that answers the question.
So thank you very much. So
there is one question in the chat.
No, we had it.
Oh, okay.
We had it, so you can, if someone has more questions, you can go in direct communication via the DVCon platform to Vishnu as well. So at that point in time, I would like to thank you. Like, I can just make an applause on behalf of the others, basically. Thank you for the time, and we would jump to the next presentation and speaker. Thank you very much, Vishnu. So, next topic is reuse of system-level verification components within chip-level UVM environments. And the speakers are Cristian Macario and Diego Alagna from MathWorks. And Cristian, I'm very happy to see you here. Actually, funny enough that Cristian and myself, we have worked in the past together. So I'm very happy here to receive you as a speaker. Hi, Cristian. Cristian.
Hi.
Yeah.
Hi, Clemens. Good to see you.
Yeah. Mentioned working at MathWorks. He has an extensive experience in embedded system design and verification, firmware, driver development, and so on. And regarding Diego, he is what I see he is actually a verification lead, right?
Yes, I am involved in design and verification activity.
Yes, design lead. Yes, so
mainly design.
Strong history in design and verification, and so I'm curious for your presentation. Again, after 20 minutes, I will interrupt you briefly to give you an indication of the timing. Okay.
Okay.
Good.
Yeah.
Yeah. Thanks for the nice introduction, Clemens, and good to see you here.
Yes. Unfortunately, not in person, but next year, hopefully, right?
Yeah,
okay.
next year.
I will go on mute and give the stage to Cristian.
All right. Thanks, Clemens. So yeah, in this presentation, we will talk about how to improve system-level verification and how to reuse system-level verification components and test cases within a chip-level UVM test bench. So here is our agenda. We will start with a quick introduction about why it is important to do verification at system level. Then we will talk about the system level design model and analysis and how it has been verified at system level. In particular, the part of the verification that has been shifted left and moved from RTL to system level. We will then talk about how system level test bench components and test cases have been reused within the chip level UVM environment. And after that, we will show how the system level design model 2 has been reused by generating RTL code from it. And we will finish by discussing the results and the planned future enhancements. So we all know that Moore's law has been slowing down over the last decade, but nevertheless, market requirements are getting more and more aggressive on performance, cost, and time to market. So how to deal with such situation? In past, single IC components were getting significantly more performant from one technology node to the next one. And this raise in performance was one of the main contributors to the overall IC enhancements from one generation to the next one. Now that performance is not scaling so much anymore with physical technology, we need to work more at system level. And each SoC component or IC component has to be optimized according to the overall architecture and take into account how it interacts with other components. So this basically means doing more simulation and verification at system level. As we said, this allows to enhance the architectural optimizations, and additionally, moving verification earlier allows to find bugs earlier and shorten the bug lead time, which ultimately leads to a better quality time to market trade-off. Now, traditionally, system-level verification requires additional resources and effort. And in our paper, we describe how to avoid having to spend additional effort by reusing system-level components and verification scenarios within UVM test benches. So in other words, we do more verification at system level, and then we reuse the system-level verification components at RTL level. So yeah, now let me hand over to Diego, who will talk about the system-level design model used by his team.
Okay, thank you, Cristian. So let's move to the design of the system level. You can see this top chip is the device we developed in ST Microelectronics that is a voltage measurement IC. You can see here the voltage input that is a measurement by an analog input stage. Then we have a sigma delta modulator able to convert the analog input to a digital bit stream. And then we have the digital part that includes a sigma delta decimator and some filtering, programmable filtering. The converted code will be read by an external microcontroller through an I²C interface. You can see there are other logic and analog circuitry that is auxiliary for this device. In gray part, you see the DUT we implemented at the Simulink level. So this main measurement unit is modeled but also verified using the Simulink platform. And inside the DUT, we have some analog models made using real numbers and the model in discrete time domain with high sample rate compared to digital clock. And then we have the digital blocks that are modeled in fixed point, bit accurate and cycle accurate way. And we will see, we will be able to generate the code, the VHDL, and implement as it is in the silicon. Some other blocks are implemented outside of the Simulink model, and in particular the I²C interface implemented with ST standard circuit. Now let's move on the system level verification part, and in particular about the test bench. Here you can see the test bench is split in three main blocks. The stimuli block that is able to provide, for example, the voltage input to the DUT, but also to give the reference to the scoreboard, the monitor block, the green one. You see that the A to D output, the code is provided as input in the monitor block, but also the voltage input as a reference. And this monitor block is able to compare the digital code with respect to the ideal conversion. The gray is the DUT and the blue is the stimuli block. If we go in deep in the stimuli block, we see that the voltage input is modeled as a constant. Then we have the A to D enable, but that is controlled by the I²C in the real device. Then we have, for example, some configuration of the filter. Other inputs, basically the gain adjustment, the offset adjustment in the real device is coming from the internal NVM. And then we have other debug ports needed controlled by another serial interface. The stimuli block is able to drive the DUT input. So for example, the analog voltage input is modeled as a real number. The configuration are controlled in the real device from I²C. Then we have some other parameters controlled from the NVM memory and other debug configuration, as we stated before. The DUT inputs, except for the V-in and A2D enables, are constant in this case. And the future enhancement would be to parameterize these constants and randomize, for example. Now let's move to the scoreboard. And you can see that the A2D code, the 16 bits, is sampled here in the sampler stage as soon as a valid is detected. This A2D is checked here by this check range block, which compares the data sampled with the correctness data range. And if this data is not inside the expected range, a data wrong is generated. This check valid block is able to filter, so to manage properly this A2D valid pulse, and in particular, it discards the first pulse as performed in the silicon. This check assertion block evaluates the data correctness when the check valid is true, using the assertion Simone block. You see this assertion Simone component that is used inside that block. And in particular, you see that a simulation error is generated at the Simulink level. But also at the chip level environment, we will have an UVM error. This is the proper configuration of the assertion block in custom with the label of UVM error. Now let's move to the reuse of the system level verification IPs within the UVM test bench. So usually the verification test cases performed at the system level need to be rerun, of course, at chip level, not only for the integration, but also for the functionality in general. The system level test bench can be reused using the Simulink UVM generation. In particular, there is a new command UVM build MATLAB command that generates a new UVM test bench equivalent to the Simulink one. Because the Simulink DUT does not correspond to the full AC, some adaptation are needed. You remember that our DUT implemented in Simulink does not correspond fully to our top chip. Here you can have just the overview of the files generated by the UVM build command. In particular, the system verilog block of the DPI DUT that executes the .so through a proper DPI. Then we have the scoreboard, the sequence with the transaction, and some of the classic UVM related block, such as the agent, the environment, the drivers, and so on. So this UVM build command is able to generate a test bench, a standalone verification environment. And in case the DUT corresponds to the full IC, it is possible to use it without modification. But in our test case, because it does not correspond, we need to adjust the environment. And in particular, for example, we can ignore in our chip level verification environment all the files we don't need. And for example, for the digital part, we can use our RTL we developed, including the RTL generated from the Simulink part. Also for the analog models, we can reuse the models we already have. Just a point about the test case and the sequences, because at the moment, to each test, so each sequence needs a generation of the full UVM test bench environment. So to have a good verification coverage, it is needed a lot of sequences and a lot of generation. And this could be a future announcement. Now let's move to the digital chip level test bench environment that we usually use to verify all the devices, the top chip you can see here. And here we have some interfaces that is able to interface the top chip with the UVM environment. And then we have also the yellow blocks, that is the blocks generated from the UVM build command. In particular, you see the sequence here in yellow that generates the transaction of the Simulink test case. Then we have the agent here that we integrate and drives the transaction at the DOT interface. Inside the agent, we have two monitors. A classical monitor that is able to translate the data output from the chip level to the real world. And then we have the input monitor able to get the VIN and provide to the predictor the expected data output. Then we have the scoreboard with integrated and generated by Simulink, able to compare the chip level output and compare it with the expected one provided by the predictor. So in order to integrate this yellow block inside the UVM components, of course, we need to remove the file generated we don't need. For example, the full environment and so on. Then we integrated the agent you have seen before and the slide before, and also the scoreboard in the chip level environment. Then we instantiated the DOT interface that has a reset and the clock. And so we need to drive properly it. And in particular, because the DOT interface has some pins that are connected not only to the top chip, but to the DOT, we can connect for sure the VIN, the voltage input, because the input of the DOT corresponds with the input of the top chip. But the other pins should be managed in another way. Because of this, we developed an interface decoder. That is a test sequence that works as a decoder for the DOT interface. In particular, we sniff the output of the DOT interface that are not accessible at the top level of the device, and trigger our internal tasks and the classes we have inside the chip level test bench to proper configure, for example, the device. In particular, for the NVM parameters, as soon as the parameters is detected at the DOT interface, we can use our internal class to write these parameters inside the NVM. And for I²C accessible register, for example, the configuration, as soon as the output of the DOT interface is detected, we automatically trigger a write access in the register map using the I²C interface. And also to read the 2D value, we are able to trigger our internal task that access to the internal register. An important point is the trigger. You can imagine that at the Simulink level, we don't have the auxiliary circuit. On the other hand, you can imagine that our device has, for example, a power up. So in order to start the Simulink generated sequence, we inserted a manual trigger to be generated after the power up and synchronize the generated sequence with the internal power up. Now let's move also to the reuse of the design part. And in particular, in this block diagram, we are talking about the green block. For this green block, we have reused the digital part as it is. We used the add-on HDL coder that is able to generate the RTL code. This is possible because we implemented this part in a bit accurate way and also cycle accurate way and in fixed point.
Diego?
So, yeah.
This is Clemens. You spent 20 minutes, so you have 5 minutes left. Thanks.
Okay, thank you. So in the end, both the Simulink test bench components and the design models can be reused at chip level. You can see here just the snapshot of the generated code of a single block, in particular the entity and the architecture. You can see this RTL is fully synthesizable and implementable in the silicon. What are the advantages of this RTL code generation? Of course, we can avoid some human errors in converting the Simulink models to RTL. For sure, we can also ensure the alignment between the Simulink simulation and the digital simulation, for example, in Cilium, cadence simulation, and so on. And we can so anticipate the bug fix at the system level. So if we fix the bug before, the workflow efficiency results improved. So now I let Cristian to finish with the results and the future announcement.
All right, thanks, Diego. So let's now talk about the results. The RTL verification time has been cut enough thanks to the reuse of Simulink collaterals. We avoided the application of effort between system level and RTL level verification. And we also saved RTL coding time by generating RTL from the Simulink design model, thus reducing the chance of human errors, as Diego said. And we finally ended up with a single source of test cases and design models with associated advantages. Yeah, here are some future enhancements, how to further improve the presented workflow. So first, we want to simplify the integration of the generated UVM components within a chip level environment, especially the way of interfacing generated components with chip level drivers like I²C driver described by Diego has to be reviewed. Then we need to find an efficient way to manage the test cases that are currently run sequentially one after the other, and there are two ways to improve this. As Diego said before, the first one is to have some multiple Simulink test benches, each of them generating a test case. And the second one is to use Simulink parameterization capabilities to allow the test bench components to generate different scenarios. And a third way, not listed here, is to use a mix of these two approaches. Next slide, please. Okay, no, yeah, randomization, yeah, right, sorry. We still have, yeah, we also want to introduce randomization, and also here we have two options. One to do it in Simulink or to use MATLAB and Simulink capabilities. And if you want to know more, take a look at our paper. All right, some conclusions. So in order to enhance the way we optimize the IC architecture, we need to shift left part of the verification and move it to system level. And I guess this is something that you probably already know. Shift left is was a big topic also this year at DVCon. And in this paper, we have shown that moving verification to system level doesn't necessarily mean more effort. things as we described, system level verification IPs can be reused at RTL level. Very similar to what was described before in the previous presentation. And we can avoid application effort even more by generating RTL from the system level design model. And on top of that, this workflow allows to detect bug early at system level before going to RTL and reducing the bug lead time. So I think we are done and on time. Thank you. Thank you very much for your attention, and we are happy to answer your questions.
So thank you very much, Cristian and Diego. So we have 5 minutes left for questions. There's already one. So which is, what is the difference between system and chip in your context? They seem to be referring to the same scope. It's a question from Jakob Engblom.
Yeah. Diego, you want to take it, or do you want me to take it?
As you prefer. You can start, of course.
Okay, so I think here with system level, we intend what has been modeled within Simulink, which is a subset of the IC level. So I think Diego described that stuff like IC bus, IC I2C interfaces are not modeled in Simulink, for instance. Yeah, Diego, feel free to.
Yes, in the flow, usually we implement the algorithmic part, for example, in the Simulink, because it is simple to simulate the analog, the digital, and so on. So let's call it system level, because we have the analysis of the system. Then if we implemented it and we obtained the good performance, we will move to implement it in the silicon and in the chip lab. So you can see that we can anticipate this verification and also the bug fixing at the first part of the flow.
So Jakob Engblom is asking back. So basically it's a Simulink-based system, it's a subsystem in the chip, and the test cases for the subsystem are used in the full chip case, question mark. Can you confirm his understanding?
Yes, correct.
Okay, what else?
Yeah, and maybe I guess the part that was modeling Simulink, I think was the core part of your C, right, Diego? That's where the added value is.
Yes, correct. That it is usually implemented in the first part of the flow, when we need to have the performance, of course, of the device.
So I will have a question as well, Cristian. So, which is always an issue when things are generated. So the benefit of generation is clear in terms of automation, but what is often an issue is how to keep things consistent. So when you have, let's say, a bug or something you need to fix in the generated code, in the generated UVM, how do you do this? Do you do the update in your model and regenerate, or do you then create deviations of the generated code, like a small branch?
So I think this is the first option. I think Diego can explain more.
Yes, usually we will regenerate again. So we fix the design at the system level and then port into the chip level, the blocks.
And is it then a quick regeneration, or does it take a longer time?
No, very quick, very quick.
Okay. Okay, so basically your master source is always in the model, and you just, like with the compiler, you regenerate then the
Yes, yes. The flow is very fast.
Okay, thanks a lot. So 1 minute left. one last question, if someone has one. Okay, here's another question. I will read it. I think as well, yes, from Jakob. So the relationship between verification and architecture. To me, when you do the architecture, you want to play around and try things with a lot of freedom. This is different from the actual implementation that should be fully verified. I mean, you do not want the architecture to be constrained by the structure of the test bench, ? I think this is an interesting and very good question, because my other question would be in a similar direction. So when you reuse the things on the two levels, typically you try to achieve two different things. And this is how I understand the question from Jakob as well. So does it really make sense to do the same type of tests on both levels, on the system and the SoC level?
I think the two scopes are different. So at chip level, we usually perform more simulation, of course, because the scope is different. So for example, you can imagine you have an MBM and you can verify all the connection to the top level. Here in this flow, we need to port into the chip level all the simulation we already done at system level. Because for sure, the system level verification should be replied at chip level. So here, usually in all the flow, we made again the test to cover it at chip level. So for this part of the test, now we are able to save time.
Okay, thanks a lot. So let's give a little applause to the two presenters. Thank you very much. And again, to the audience, I think by the platform from DVCon, you can directly contact the speakers as well by a direct mail or chat. So if you have further questions, take this chance. Thanks, Cristian. Thanks, Diego. And now we come to the last presentation, which is a novel approach to functional test development and execution using high-speed I/O. One presenter is Schulze-Westernhorst Markus, or Markus Schulze-Westernhorst, which works for Advantest Europe. And he has significant experience in pre and post silicon validation at different SoC companies. The second presenter, Jörg Simone, I don't have a CV from him, but Jörg, I think we know each other, right? So he is, I think you are an application engineer at Cadence, right?
This is correct, yes.
So we have met several times, especially on the formal verification aspects, right? So, so it's a collaboration between two companies, how I understand it, and I'm curious to see and hear the presentation.
So thank you, Clemens, and thank you everyone for joining our session about a novel approach to functional test development and execution using high-speed I/O. Looking at some short and long-term studies, there is vivid and continued growth to be expected in target applications such as mobile phone processors, high-performance computing, machine learning, as well as network and cloud computing. These new developments bring challenges of increasing design complexity along different vectors, as shown by the two depicted graphs. Moore's law indicates an ever higher gate count integrated into a monolithic die, while the studies on the right nicely shows additional vectors of increasing design complexity, for example, technology node evolution, advances in packaging technology, and a continuously increased integrated functionality. Let's have a look what these vectors of increasing design complexity mean for classical ATE test programs. There are quite some buzzing headlines indicating chiplets as the hottest trend in semiconductors, which was enabled, amongst others, by previously mentioned advances in packaging technology. One reason for the increased use of chiplets is the reduced cost per chiplet achieved by a higher yield at a given defect density. On the other hand, multiple chiplets integrated into a package leads to challenges for production test, because chiplet interconnects are not accessible at the chip boundary. New technology nodes are introducing new failure modes on top of the classical stucket and shorts, such as bridges and necks, which may lead to unpredictable coupling between the signals, requiring new means of test on an ATE. And even though a high ATB-G coverage of 99.5% on a SoC with 2.5 billion integrated transistors could be achieved, it leaves tremendous 12.5 million transistors untested, also requiring new means of test on an ATE. And last but not least, leading-edge devices with multiple integrated CPUs allow concurrent scenarios to be executed, which are hard to be covered by classical test pattern approaches. So altogether, we believe that functional test content is likely to grow in a typically scan test dominated ATE test program. To bring additional and advanced functional test content to an ATE environment brings challenges to the ATE world due to fundamental differences between functional and classical ATE test content. Both are often developed by totally different teams in different environments, as shown in the graph on the right-hand side. Furthermore, functional test is usually executed as embedded software, downloaded by logical interfaces such as USB or PCIe, while production testers usually operate based on test patterns utilizing parallel physical interfaces. In order to bring functional tests to a production test environment, barriers such as vector conversion, vector memory shortage, as well as no native HSIO interface support have to be overcome and require a novel approach to functional test development and execution using high-speed I/O. But before introducing the new approach, let's take a little time to look deeper into three selected problems. Even simple SoC architectures, as shown above, allow for endless potential test paths, which are increasing further if you parameterize the potential actions. If you, as a validation engineer, based on the architecture analysis, create a manual test plan and report passing test cases over time versus a required target curve, you will have difficulties answering the question about your functional coverage. Secondly, functional software-driven self-tests are typically developed as a piece of software, are compiled, downloaded, and executed in mission mode on the DUT, and are terminating with a pass-fail verdict. This is fundamentally different than the black box approach of an ATE test content with its pre-calculated driving vectors, which are stimulating the DUT. The result is calculated then based on a comparison between received and expected vectors. This leads to the problem that if functional test content is needed to be executed on an ATE, it needs to be converted to vectors, which historically was done by RTL simulation and strobing the chip pins. No matter how you convert the test content today, it's an unwanted step, and you would ask the question, can this pattern conversion be avoided? The third problem I would like to highlight is the limited debug capabilities of functional test on a production tester. Usually, the debugging of failures on an ATE consists of signal level or waveform view analysis, which is very hard to map to the software semantic of a functional test. Thus, debugging of functional test content on an ATE is often a team effort of design or validation engineers and production test experts, including the repetitive and time-consuming loop of resimulation, pattern recreation, and re-execution. On the other hand, a native software analysis environment consisting out of software traces and the seamless usage of a standard in-system software debugger like Lauterbach would be desirable, which brought us to the question, why can't standard software debuggers be used on an ATE? Stitching all the previously mentioned problems together, we believe that the process of bringing functional test content to an ATE environment needs to be thought completely new. It needs to start with a test content creation, followed by the handover of the test content to the ATE software, which needs to control the test execution on the ATE hardware. The ATE hardware then loads the test binary into the DUT, where the functional test is operated in mission mode and returning software traces on top of the test results. The flow will be completed by the integration of comprehensive software trace analysis and integrated in-system debug capabilities. On the next slides, we will show you how PSS-based test content seamlessly can be handed over to an ATE and executed there without a pattern conversion step. We will show you how we can control PSS test parameters at runtime on the ATE to explore the DUT and how we can increase the coverage. Furthermore, we will show you how functional test content can be downloaded to the DUT utilizing native high-speed interfaces and how analysis and debug of functional test on an ATE can be achieved in a native software analysis environment, avoiding time-consuming debug cycles. And with this, I would like to hand over to Jörg, who will start his explanation with the test content creation step.
Thank you, Markus. So let's continue with PSS. So the acronym PSS stands for Portable Stimulus Standard. You got a kind of more detailed introduction with the previous session at the very beginning today afternoon here. I will stay on a very high level here. So the goal of this standard is to create for SoCs or for subsystems a rich set of test scenarios in a way that those can be reused. This is achieved by a PSS model that is defined once with the characteristics that it can be shared between multiple projects or even between multiple teams. And exactly this was the main idea for our project: reuse verification solutions. That means reuse well-defined and portable PSS models in the ATE world, which have been created and tested already in the pre-silicon world. In the lower box here, not all, but many of the very popular and mature pre-silicon verification techniques are listed. And with our project, we describe here, we try to map those techniques from the pre-silicon domain to the ATE world. Next slide, please. To be able to work with the reusable PSS models, a human interface is available. Here you see on the left box an UML diagram with the related control knobs. The user can compose scenarios, he can add constraints, he can set individual attributes for the predefined PSS model. So this is also possible to control in the batch mode as well. Out of the PSS model, code is generated, and during the execution of that code, functional runtime coverage will be collected. This you see, the collected coverage you see in the middle box. This functional coverage based on constrained random data is a major add-on to the ATE world and increases significantly the quality of the statistical analysis part in the ATE flow. The DUT becomes more and more a gray box for the test engineer. The workflow you see on the right side will be explained with the next slides. Please click. An important topic in the ATE world is the question of how to manage hundreds or thousands of tests in the most efficient way. The question is, how can we easily hand over many tests from one to the other team or share it between multiple company locations? And our answer here is a kind of bundle or container. We call it FDAT, that contains all the information that is required to run a single or multiple tests. The FDAT is a well-defined infrastructure, including the required test binaries, precompiled, and parameter sets, and optional source code documentation and even statistical analysis tools, etc., etc. So the FDAT container itself, it's not a fixed format, it's an extendable format. Please click to the next slide. Now, after everything is prepared with the FDAT container, we come to the execution phase. With multiple FDAT containers as an input, it's quite easy to step through a complete ATE flow. The ATE engine will be instrumented appropriately based on the content of the FDAT container. And then the ATE will be started and will communicate via the high-speed I/O interfaces with the DUT. Depending on the individual needs of a project, it's possible to work in an A, interactively mode for debugging or analysis cycles, or B, work fully automated in a high volume production mode. So regardless in which mode, the flow as shown here will be always the same. Please click. One of the new introduced features is a smart solution to be able to change parameters of the test executed on the DUT without the need to recompile the complete test. The delivered software as part of the FDAT container is prepared accordingly already to make this possible. That means there is a major static part of the software that will be loaded to the engine only once. And there are many small software pieces that represent the parameter sets that will be exchanged on demand by the ATE control software. And this will be done automatically. And this enables a high grade of automation for systematic DUT behavior testing that was not available out of the box before. Yes, please click. Next slide. Yeah, we have seen how the DUT will be controlled and how the input-output data are processed. Now let's introduce the analysis part briefly. On the left-hand side, you see an UML diagram with a multi-core cache coherency use case, what is defined here. The model contains multiple loops for different parameter sets. The parameter sets itself represents multiple variants for the cache setup in this case. All is encapsulated with the explained FDAT containers and have been executed already. So the provided output data are supplied to the test parameter exploration post-process, what you see on the right side here. And important here that is that the very expressive SHMU diagrams combine now two different dimensions. So one dimension are the data what are provided by the functional PSS model. So like status of the cache, memory size, executed loops, all is defined as part of the PSS model. And we have also in the other dimension, the data based on physical parameters like clock, voltage, etc., etc. So this combination is a kind of new quality for those kind of diagrams. And this is also the end of my part here. Please, Marcus, continue. Thank you.
All right, and thank you, Jörg. Now let's turn the focus to the test development and execution part of our approach. Comparing the classical approach you see in the upper part with our novel approach reveals some important enhancements. Instead of a standard digital ATE card, we are using a smart compute instrument with its own memory, supporting native high-speed interfaces. With this newly developed card, we can achieve two important improvements. Firstly, we can offload the vector memory by moving the functional test content to the new smart compute instrument. Secondly, we can download the functional test content of the FDAT container via a template test program in high speed over a low pin count interface directly into the DUT memory, saving us the pattern conversion step. With the help of our new test scheduler software, we can control the execution of the functional test content and can, for instance, switch the DUT after the test case download into mission mode and can afterwards start the functional test execution on the DUT. During the test execution on the DOT, the test scheduler maintains the high-speed interface operation and collects software traces from the functional test case for a post-mortem analysis in the new activity trace viewer. It allows visualization of the collected traces, which can also be exported, e.g., for a deeper analysis to a scenario viewer. In addition, we implemented a hook that the standard software debugger can be started, allowing seamless in-system debugging of the test case code executed on the DOT. This is achieved by the JTAG interface support, which we integrated into the smart compute instrument. And how this analysis flow will look like in real life will be shown on the next slide. So let me share with you how we realized the native software analysis and debug environment on an ATE. Just assume you use a standard SHMU and explore the DOT corner cases via parameter variation of a single test case. The SHMU view allows for an easy to interpret test result overview where failures are indicated by a red color. The software traces, which are collected during the test execution via HSIO interface, are accessible directly from the test case result shown in the SHMU view. The software traces are displayed in the newly developed activity trace viewer and visualize test internal states in a human readable format. The test internal states should help to identify the root cause of the failing test and in best case are good enough for this purpose.
Marcus?
Yeah, just another 5 minutes. Thank you. If the root cause remains hidden though, you may export the activity trace and use them in an external scenario viewer, which allows to perform a more in-depth and synchronized analysis of the original test case sources with the collected activity traces. Furthermore, the scenario viewer allows in waveform-like view to perform a graphical analysis of the test progress. The idea is to derive a reasonable software breakpoint of the test case code. We integrated the standard Lauterbach Trace32 debugger in a way that a synchronized execution of ATE software and software debugger is seamlessly made possible. We can directly from the ATE environment start the debugger and debug the test case code on the DOT. And this allows to perform all the standard debugging steps like stop, step, analyze, and resume. And with this, I would like to share the results we were able to achieve with our novel approach to functional test development and execution using high-speed I/O. As a DOT, we used a Xilinx ZCU102 FPGA with 4 Cortex A53 processors, an MMU, and some memory. And for the high-speed interfaces, we used an USB port, and for the JTAG, for the debug, a JTAG interface. For this FPGA, we realized a multi-core test scenario modeled in PSS, which implements the previously described cache coherency testing. Based on the implemented parameters, such as cache enable, yes, no, and memory access size, we were able to set up a SHMU on the ATE and could sweep the memory access size versus the DOT configuration, which enabled or disabled cache. The test case was then executed on the DOT with the mentioned parameter variations. A test case internal timer measured the memory read and write times and returned the measurement results via the software traces. The parametric results collected could then graphically be analyzed as shown in the graph on the bottom right. For instance, the gain by enabling the internal cache could be analyzed and how it develops over different memory block sizes. So altogether, we managed to implement a complex multi-core test case for the FPGA DOT with the help of a PSS-based test case modeling. We varied the implemented parameters at runtime without the need to recompile the test case directly on the ATE. And finally, we used the device internal measured results to explore the performance of the DOT. There is a second major benefit we were able to accomplish: the fully and tightly integrated execution flow of test cases, starting from their creation over the execution on the SoC and stopping at the integrated analysis and debug circle, allows to execute a full execution circle in just minutes. Compare this with the time-consuming execution circle, including all the additional steps needed because of the pattern conversion. In addition, to this automation capabilities of an ATE lays ground for efficient functional characterization. In the central picture, you'll find snapshots of all parts of the novel approach and how they correlate to the previously described parts of our approach. Just to quickly mention, we based our novel approach on following products from Cadence and Advantest. The Cadence Perspex system verifier was used for the PSS modeling part, the Advantest V93K ATE hardware platform, including the newly developed smart compute card with SmartTest as the ATE software controller, was used to download variety parameters, execute and analyze the PSS-based test cases. And for the external scenario viewer, we used Cadence and Dargo. Our novel approach, in addition to previously mentioned results, enabled new ways of work and cooperation in the ATE environment. With the help of PSS, a tool-based functional coverage statement could be generated. In combination with the ATE capabilities, it's possible to explore the coverage of the design beyond device internal stress conditions in direction of environmental stress, such as voltage, temperature, to further increase the validation coverage. The PSS model is independent of the verification platform and allows for reuse of the test content from pre to post silicon. Also, the way validation engineering is done may change. Known tools to create and execute functional tests also from remote locations, including the integrated analysis and debug capabilities, allow for easy co-working across team and location boundaries. And finally, transferring test cases into production test or characterization can be achieved smoothly. Due to the high automation capabilities of production testers, it's constantly possible to monitor the quality of the complete test set. And this brings me to the conclusion. In our project to realize a novel approach to functional test development and execution using high-speed I/O, we were able to combine the benefits of design verification tools with the capabilities of an ATE system. This increases design coverage for production test by bringing functional coverage and constrained random testing to the ATE. It allows combining test and environment parameters variations for more in-depth design exploration. And finally, functional test does not occupy vector memory, which allows to increase structural and functional coverage. On the other hand, our novel approach reduces the effort for functional test on an ATE by the native execution of functional test as embedded software, as well as by the native software bring-up and debug environment support. And in total, we believe that with our novel approach, substantial improvements in time to quality and time to market can be achieved. And with this, I would like to say thanks a lot for your attention and would like to close this presentation and open the Q&A session.
Okay, thanks a lot, Markus and Jörg. So the stage is up for questions. You can talk, unmute your mic, or you can write it into the chat. My question would be, have you applied this to the A53 ARM core system, which you have shown only, or have you applied this scheme to other SoCs?
So basically, what you see is something like a proof of concept for this novel approach, and we use this, the described DUT or the described Xilinx ZCU as our proof of concept vehicle.
Okay. Thanks.
Yeah, the process or the approach will be the same regardless which core is used as a demo core or then in production. So there will be, it's only a question of implementation.
Right. So it's not restricted to it. We believe it's seamlessly transferable to any other DUT.
Okay, so if we do not have another question left, I think we can close the session. Please don't forget to vote for the best paper and best poster award. The link has just been listed again in the chat. So you find the link in the chat. And let's close with a little applause to the presenters. Thank you very much for your attention. And I hope that we all see each other in live physically next year, right?